Hello, Mr. Wickham here. We're going to be talking about charges and the fields that they produce using a PhET simulation today. So why a simulation? Well, charges are really difficult to handle and they're almost impossible to measure accurately in a classroom setting without really sophisticated and highly precise equipment. And so a simulation avoids these and other problems. I mean, you imagine a charged object, you touch it, and you've now grounded it out, so you've changed the actual value of the charge just by interacting with the equipment. So you can imagine it's difficult to do in a real lab. So we are going to do a simulation, which allows us to see what's going on in a way that is going to be much more useful to us and much less fraught with difficulty. All right, so we're going to first navigate to the PhET website. And that's phet.colorado.edu. I've got it pulled up here. The charges and fields simulation is found under physics and electricity, magnets, and circuits, charges and fields. It is an HTML5 simulation, so it should work just fine in most modern browsers and also on most smartphones. So that's great. No extra plugins or anything required. Once you have it up and running, you should notice that there's a lot of there's a list of options and tools over here on the right-hand side. The charges and sensors are located down here on the bottom, and a big reset button down here on the bottom right. So you could use this on your tablet, you could use it on your phone, you could use your laptop, desktop, doesn't matter. So put a couple of charges out here. We see that there is a electric field that is shown emanating away from the positive and going into the negative. That's the direction that a positive test charge would feel a force if it were placed in that area. So it's going to be repelled by the positive, clearly, and attracted to the negative. And so that's the direction that we get for the electric field. The magnitude of the electric field is shown here as the brightness of the arrow. Notice that it's getting weaker and darker as you get away from these charges. You have the option of showing just the direction if you don't actually care to see the magnitude indicated that way. Or you could actually turn the whole thing off altogether and just not show it. The voltage will show you the actual voltage as a red and blue gradient around each of your charges. Remember, the voltage is a measure of the amount of energy that each unit charge would have if it were placed in that area. So clearly the brighter areas have more energy per unit charge than the darker areas around. And if I add more charges in one area, I'm effectively increasing the amount of charge and increasing the voltage and the resulting field around it. Let me grab those and pull them back off so we can take a look at the values. Now, what does that mean, values? Well, if I put a sensor up here, then it's going to tell me with its arrow the magnitude and the direction of the electric field as a vector that's changing length as opposed to changing brightness. So again, I put the electric field back on, and you can see that the direction of the sensor's electric field is going to be perfectly aligned with the one that's already displayed. But the value of the magnitude of the electric field is shown as the length of the arrow, which gets quite big as I get closer and closer to each of the charges, going away from the positive and going toward the negative. The values checkbox allows you to turn that on or off, showing the actual numerical values of that sensor's reading of the electric field. Okay. The grid line is a 10 centimeter grid. So each of these little boxes is 10 centimeters by 10 centimeters, and so you could align your charges very nearly perfectly on those and be able to make some pretty precise measurements without too much difficulty. If you need to make some measurements that are not on the grid line, or you're not using the grid, then you can use the tape measure and be able to measure distances on this graph or on the screen pretty precisely. So 238 centimeters or so. Drop that back off. This is the equipotential tool, and it is able to measure the voltage value. So just like that voltage shows that, notice as we get closer in, the voltage is getting bigger and bigger and bigger. The amount of energy per unit charge is what the voltage is, the equipotential, or the electric potential. And the equipotential will actually show me lines where all of these lines, all of these positions around here have the same amount of electric potential, 4.5 volts. They're all connected, and so you can draw these lines at different voltages And they behave kind of like the contour lines that you might find on a topographical map, which will connect all the points that have the same elevation above sea level. You can see the contour here. Going back to this, all of these points have the same elevation above 0 voltage, or as you get closer to the negative, you actually have negative voltage. And so the negative charges are more like valleys or holes in the ground in the same topographical analogy, and the positive charges are more like mountaintops. Okay, so if you click the eraser button, it clears all of those, all of the equipotential lines that you drew, or if you draw a couple in and you change the charge distribution in any way, then all of the lines get erased. Also be aware of that. So if we have a couple of positive charges and we draw an equipotential line, you notice that it's kind of like having two peaks at the very top of a mountain with a saddle in between. I don't know if you're familiar with hiking or topography or topographical maps of some kind. So you could create your equipotential lines. All of these lines connect the dots that have identical values of electric potential. All right. So we'll be using the simulation to examine electric fields and the charges that generate them and the electric potential that gets created as a result of the charge distribution, and answering some questions and doing some calculations and predictions and seeing if our predictions match up with what the simulation shows us. All right, well, best of luck to you.